All right, so welcome back to the last session of today's school. Just a reminder, tomorrow we will meet again here from 10 to 12 to learn more about discuss research. Okay, take it away.
All right, thanks. You can hear me okay? Yeah. Okay, so this is a follow-up. This is with Zhao Yang, my former student, who was also a collaborator on the previous work. And this is taking the same problem, but now we're doing a multi-D version. We're going to take, so it's inclined flow down a ramp, but now it has sidewalls. And yeah. Okay, and what are we looking for? Well, there was no multi-D theory. So we were just looking to see what we could find, what the differences were. But I did have one motivation from the beginning, which was to understand what's called herringbone flow, which is doubly periodic flow. Can't exist in 1D. So that would be something new to see. And let's see. Okay, so here's a picture of the full water wave problem on a ramp, and it would have, so this would be incompressible incompressible Navier-Stokes. It would have no slip boundary conditions on the wall. That would be pretty tricky. And okay, but we're making various simplifications. And well, I'll go to the equations in a minute. But basically, we're looking at 4 building block kind of solutions that you see. One would be this laminar flow, just constant height flow down the ramp, and nice quiet day. The rollway, the shocks that we already talked about, which would be, here I've drawn a smooth one, but we know it can sometimes have a subshock discontinuity inside. The roll waves, here they are, down here. Where is it going? Okay, and then here's the new one, which I couldn't draw very well, but it's got a doubly periodic pattern, so it sort of looks like the roll wave at these crosshatches that I've drawn. Each one is a little shock, and they form a diamond patterns. Okay, well, and yes, I should say, now that I know that I can find these things and look at them and send my kids out to get them. Well, we saw plenty of these, but we saw more of these, right? This is what you see when you go outside to a stream or something wider with real multi-D effects. So we were very hopeful to see that somehow, but we didn't know how. Some kind of bifurcation, we thought, from the roll waves, maybe. Here are the equations. Okay, so we're going to definitely stick with the inviscid equations. First of all, we've seen that that's a good thing to do already in the 1D case, but all the more here because we don't want to deal with any boundary layers on the walls. And we don't have to, because we'll just put slip conditions here, just wall type boundary conditions that the fluid cannot exit through the wall. And that's all we need. Okay, so there's an X. X is the direction of flow, of incline. Y is the orthogonal direction. We have the same Froude number, F. And okay, everything the same. Almost, except what's different is, okay, so obviously in the Y direction, we don't have any influence of gravity. Gravity is pushing us only in the X direction. So our relaxation term here, so U is the velocity in the X direction, V is in the Y direction. So the equilibrium value for V is 0. It doesn't balance with H. So our equilibrium system would be with UV equals H to the 1/2 and 0. We would plug those into the first equation, and we see that we get the same one-dimensional dx of H to the 3/2, but this would just vanish. This would be 0. So it's a pretty degenerate equilibrium system. And here it is. Okay, so, and again, that's going to give us something that we expect for near equilibrium and F less than 2. It might be pretty good for a small amplitude. But we've already seen, even for 1D, that's not really going to happen. Okay, we're again reviewing hydrodynamic stability of the laminar flow. That's F less than 2. And we're in the 3 to 10 regime. So we're not there. We have these Dressler waves. Okay, so now let's see. So basically, this is what we're looking for. I didn't talk too much about this, but this is what the Witham equation is modeling. It says, okay, we have, I want to go back. Okay, so we have all these solutions are parameterized by the Froude number, F, the wavelength, and the minimum height. And so that's a number of parameters that determines the waves. So here we're going to try to look at slowly varying average height and wave number, and then quite possibly and a slowly varying phase shift. But these waves have a very these waves are varying on period X. And if we make this assumption, then we get these equations. Okay, again, that would be completely valid for the viscous case. Here it's a bit of a guess, but here's what you get. Now the curl of the wave number must be 0. And here's what our solutions look like: k dot x plus omega t. And okay, so with this setup, a single planar roll wave, like the 1D roll wave just extended in y, that would correspond to a constant parameter solution. It would be just one value of h bar and k. So well-posedness or hyperbolicity of this equation would be a consistency condition for 3, and it's a 2-variable system varying around the constant state. Okay, but we're going to try to, as we've seen, it's better to work with the exact eigenvalue analysis. It's actually simpler than the formal asymptotics to do it exactly. And so we're able to, so what have we done? Well, I just told you in the previous talk, we got explicit low frequency stability condition, a full stability diagram for roll waves, efficient numerical methods, but all in 1D. So we wanted to go to 2D. Okay, so I think this is interesting. Multi-D in general is interesting, just to go to multi-D, but also, and especially because here we have discontinuous relaxation fronts. And well, you know, for example, in the inviscid theory, going from 1D to multi-D, that was just a major landmark work of minor. This is really, sometimes there's a big jump. Here we have 2 things to help us. 1, MITA already did it. And 2, it's not really full multi-D. It's in a channel. And that means in the orthogonal direction between the walls, you don't have, if you were to Fourier expand, you're doing a Fourier series, not a continuous Fourier expansion. So you have discrete modes. That's easier. More like it's kind of like 1D with other modes slaved to 1D. So there is some help. Okay, but we're really hoping to understand selection, like which waves are going to come out and when, and to understand these herringbone flows, which hadn't been discussed. And maybe I should mention, whoops, as regards herringbone flow, there's some very nice recent work of Ian Tice and collaborators on herringbone flow, now giving rigorous bifurcation results on existence. Fantastic. Okay, so we have, okay, what about the hydraulic shocks? I'll just review the 1D stability. I didn't completely tell you the whole thing. So when F is less than 2, there are 2 kinds, smooth ones and subshocks containing ones, and they're both monotone. And they're both stable with respect to, say, H3 perturbations. That is, so what do I mean in that case? So H3 would be to the left and to the right, perturbing to the left and right of the shock, but not at the shock. And a big part of this stability theory is to show that singularities don't form out in the flat, that there are no new singularities forming. It's kind of the opposite of our lectures of this morning. Even though there is a big singularity, and obviously that did form, but once it's established, it's going to just rule and there will be no others. So that's something that you have to show. Okay, but then for F bigger than 2, there are actually also are some shocks, and they are stable, but in a more restricted sense. I already mentioned to you that homoclinics couldn't be stable in the first talk because the end states were not stable as constant solutions. Same thing holds here because F is bigger than 2. How is it stable? Well, it's stable with respect to a weighted norm. That's called convective stability. And the basic idea is that as disturbances come in near the shock, well, that all important disturbances are swept into the shock and then eliminated by the near field behavior dynamics. Okay, and you can show that by working on a weighted norm. Okay, so it turns out all 3 of these can be proved in 1D rigorously to be stable. Okay, so now, what's the other result that's known? Okay, so my grad student Bong-Soo Kwon, who's in Korea and doing great, he did a fantastic thesis work. He proved that if waves are small enough for general relaxation systems, not only this one, that they would be nonlinearly stable on the whole in the whole plane. Okay, and one could adapt that easily to the channel. But actually, spectral stability was never verified. He said, if you have spectral stability, then it's true. Okay, so there's really no analytic spectral stability result in 2D for any case, and that's still true, basically.
What do you mean by general relaxation?
Oh, so just just in the same way that we had general n by n systems in the first lectures, I would just take a general n by n system. Maybe I'll just write it down here. So so same kind of system. So we take psi. Okay. So it would be a system of this form. Physically, they almost always have. So this is like some kind of reaction term, and it has a constant left kernel. Like if I take the Jacobian of this, it's constant left kernel. This is assumed. So we'll have dr d psi. Let's see, yeah, dr over d psi. Real part of the spectrum, strictly less than 0. So this is pushing toward, let's see, psi 2. It's the derivative with respect, so I'll write psi as psi 1, psi 2. I've got this block decomposition. It's the derivative with respect to the second one, has to be forcing this toward an equilibrium. So that's the basic definition of a relaxation system. And we have that here. Maybe that might be worth going back to. Let's just look at our system. There it is. Okay, so look at the right-hand sides. So the psi 2 would be U and V. Okay, and here we see that the Jacobian is, well, not quite diagonal, but diagonally dominant, and it's just -1 or negative u squared, or velocity squared. Sorry, velocity, amplitude. Okay, so. It comes, sorry? No, well, no, this is part of the modeling, the asymptotics to shallow water. Yeah, so and well, it's basically saying, oh, okay, no, it's better than that. So it's this Chasey turbulent friction that the turbulent friction should oppose your direction of motion and be proportional to velocity squared. And that's exactly what we have here. Yeah, that's really the answer. And then, okay, and then the other term, the H, that's just gravitation is pushing it in the X direction only, in the fall line. Okay, so, right. Okay, so we're going to just, first step is to just recover the, just rewrite the same picture of nobla. We've got this eigenvalue problem. Again, it's going to be on a periodic cell. Now it's periodic, sorry, it's periodic in one direction, in the X direction. In the Y direction, it's a little funny. What is it? Because all it says is that it says that V vanishes on the boundary. That's all. So that's something that's a little interesting. What's that doing? But I'll tell you later what that does. But for now, we just put that in as our boundary condition. And then we have, at the right end of the cell, we have a linearized Rankine-Hugoniot condition. And that completes completes the model. Okay. Whoops, what did I do? Oh, sorry. No, that was for the profile. And then this is the linearized Rankine-Hugoniot condition. So, okay, so psi is the perturbation, the linearized perturbation of the shock location. Psi depends on Y and T. Okay, so this is what you get. There's something interesting here. Is that what? Okay. It's a little different from, yes, let me go one step further. Okay, so now, sorry, that was the nonlinear equations. After linearization, we get an interior equation that just looks like any linear variable coefficient hyperbolic problem. It's got a balanced source term for the relaxation forcing. And then here's the linearized Rankine-Hugoniot. Okay, now it looks different. It looks different than the Maida theory because we have derivatives of the traveling wave coming in here. And that's new because in the inviscid theory, the shock is constant to either side of the discontinuity. Any derivatives of the background profile would be zero because they're constant. Here, they're not zero. Okay, but it's not that new. This is very much like detonation. In detonation, there's always there's a combustion profile and followed by a shock and then constant. And that was looked at long ago by J.J. Erpenbeck. He was a real pioneer in combustion theory and shock theory. Okay, so you put these together and you observe. So this term that looks bad, it's not so bad. Because if we look at the profile equation, we actually know that this could be replaced by just the source term, R at U bar. We get rid of that derivative, which doesn't look so nice. And now it just looks like this. It's just a jump. Okay, a few things that happen. So lambda is d by dt. Eta, I eta is d by dy of psi. And then R just goes in there without a derivative. And then what's left is this was jump in A times V hat. So V hat is Laplace, basically Laplace Fourier transform of V, capital V being, now capital V is all the vectors, H, U, V, little h, capital V is little h, little u, little v. Normal modes are decaying solutions of 9. By decaying, I mean that they decay, let's see, what do I mean? Oh, sorry. This is for this is for shock waves. I'm so sorry. This is not the periodic cell. This is for shock waves. So they need to decay out at infinity. All right. So spectral stability is equivalent to no normal modes with the time frequency lambda having positive real part, because that would be an exponentially growing solution. We can't allow that. And then we already know from the work of Erpenbeck, Kreis, and Maida, there needs to be some extension to the neutral real part of lambda equals 0. We really need that there be no eigenvalues there as well, except at the origin, and a bit more, which I won't discuss. But sort of like Maida's uniform uniform Lopatinsky condition in the inviscid theory. Okay, so now, if we assume hydrodynamic stability of the end states, which would be necessary for L2 or H2 stability, the basic stability, not convective, then it turns out it's pretty easy to see that the dimensions of the manifolds of decaying solutions at plus infinity and minus infinity are independent of lambda in this region, real part of lambda positive. And they are the right number to give, so that there should be a unique solution, so that there should be no, a unique solution 0 of the eigenvalue equation. So only trivial solutions, unless a certain determinant vanishes. And that determinant is called the Evans-Lopatinsky determinant. It's very much the same as in, but simpler. It's the same as in the previous talk, which was for periodic problems. Now we've replaced the Bloch-Floquet number, which was Xi, by eta, which is an actual Fourier transform in the y direction. But it looks very similar. And this looks exactly like the stability condition for detonation, identical. And that's because detonation looks exactly like this with a different kind of R. So, but it's not a relaxation system because it doesn't satisfy the condition that I wrote there, but it behaves much like one. So some of this, there's some analogy with detonation. Okay, so, okay, stability for F less than 2. Those are the monotone decreasing ones. Okay, so in one dimension, the interior equation was 2 by 2. So a first order system with 2 variables. You can always transform that to a scalar second order problem. And that means you can apply some Sturm-Liouville theory. Some issues though, by doing that, now you get lambda, the frequency enters nonlinearly. It's not a standard eigenvalue problem, but it turns out you can use a generalization of the ideas of Sturm-Liouville, and you can prove these are all stable, and we have done that. But in 2D, now it's a 3 by 3 system. We don't have such a reduction available. It doesn't, one might hope it decouples. It doesn't. It actually, it does for smooth waves, but not for discontinuous. So back to the supercomputer. Luckily, we have IU prides itself on the supercomputer, Big Red. And by that time, Zhao was at Urbana-Champaign, and they have a Big Blue, I think. And okay, so we had a lot of supercomputers. And it took 16 days on a 64 core model to check all the parameters, but they're all stable. Okay, so we started to, okay. We also carried out these low frequency limits, like comparing to the Witham system, and there's some high, sorry, not Witham, to the equilibrium system, looked at high frequency. We can do them, but they're kind of useless. They're necessary conditions. Okay, so conclusion: the formal equilibrium model is still good in behaviors it's very far from equilibrium, but it still qualitatively works. And at this point, the only case not treated is the small amplitude one that was proved long ago by Mong-Soo Kwon to be stable if it's spectrally stable. But actually, spectral stability gets really hard to show near the small amplitude limit, which is a constant state. It would seem that should be the easiest. It's not. It becomes a very stiff numerical problem. So that's amusing. But anyway, that's not the regime we're in for the interesting hydraulic engineering problems. Okay. If bigger than 2, I already mentioned, I think, that one can have convective stability of these shock waves. All right. And, okay, so now, where could, this is the hydrodynamically unstable regime. That's where patterns can be expected to form. We're kind of hoping for this herringbone. How could it happen? We thought maybe there would be a kinking of the front, like a muck stem, something like Maida and Artola looked for in detonation, and this would somehow break apart into herringbone. But this is not at all what happened. So this is very funny to me. Okay, but here's one thing, is that, okay, let's look closer at this convective stability. Convective stability means that you pick a weighted norm and miraculously it takes bad continuous spectrum and makes it good. It modifies all the spectrum though, all the spectra, and eventually it can happen that it no longer stabilizes things. At some point, things go wrong. Okay, but where is that point? Maybe hard to see. But there's a really nice observation, quite general, which is that one can also look at the Evans-Lopatinsky determinant that we defined. And analytic extension of that is very important, especially across, up to and across essential spectrum boundaries. Okay, but at some point, that analyticity breaks down. There will be singularities. At that point, the weighted norm method can no longer work. Why? Because if the weighted norm method works, then you have extension, automatically analytic extension of the Evans function. An exponential weight, you just put an exponential weight in space, and you choose different weights at plus infinity and minus infinity, according to whatever, and then you interpolate between them. Because what they're really doing is they're trying to modify things out at the far field to fix something bad there, and they must be growing weights, so they must penalize distance from the origin. Otherwise, you have a problem when you try to go to the nonlinear theory, that the nonlinear equations will have exponentially growing weights as in the coefficients. So you really need to be penalizing distance from the boundary. All right. Yeah. And therefore, right. And so therefore, as yeah, that's all I'll say. But by this observation, one can vary. I mean, these are tricky computations. It's all linear algebraic computations, but it's a 3x3 matrix, and you're trying to find the eigenvalues and where they do certain things. It gets pretty tricky. But this turned out to be the key to finding these boundaries. So we found the boundary of convective stability, and we could find it in 1D, and we could find it in 2D. And the funny thing is that, okay, that comes next. The 2D convective stability boundary, this is the important remark right here. It's less, so effectively, if you fix the amplitude, this is just increasing the Froude number. And at some point, things go wrong. They go wrong sooner for 2D than they do for 1D. That's good for us, because that means there should be something interesting and new happening. So waves that were 1D stable will now be 2D unstable. That might signal a bifurcation. However, the thing that we weren't expecting is this is all happening for large frequencies. Usually bifurcation, we look for some kind of bounded frequency. That would be a Turing bifurcation, or something at the origin. That would be just an exchange of stability. And that's not what we see. Okay, so now, okay, so now I hope that this works. This is a time evolution study. Maybe, let's see if, do I dare go back? That was a little fast for me. I can't quite go back. It started as a Gaussian perturbation of an exact shock, hydraulic shock. And this is, you can kind of see, as in the 1D case, there's just some linear oscillatory behavior, but then it saturates into nonlinear patterns. And what are the patterns we see here? Well, right now I see some roll waves here. And then behind them, I'm very happy to see herringbone patterns. And as time goes on, I get even happier because the roll waves are going away. They're being overtaken by an invading front on the left of herringbone and on the right by the shock. And it takes really a long time. I'm sorry, I don't know how to speed this up, but after a very long time, there's only herringbone left. And so maybe I don't think I want to wait quite that long. Okay, but after a while, it's not really clear at this point, but after a while, they're all gone. And you have only herringbone left behind. Not only that, this looks a little chaotic. After a while, it firms up into a nice doubly periodic pattern. Okay, let's stop there. Oh. Okay. Although I messed with the view. Still good. Oh, thanks. Great.
You want to try to go all the way to the end?
Oh, no. Oh, no, I just wanted to stop it. Oh, yeah, you could just hit the pause. Oh, I see. I think we weren't in the full view. There we go. Oh, yeah. Now you can see the end. Yeah, looks pretty good, right? Thanks. Okay, so we thought we have found the bifurcation point. It's when 2D, the 2D convective stability fails, and then there should be bifurcation, right? But that's not true either. So here is something. So we just found it numerically. This is oh, I think I missed one. Let's go back. Yeah, okay, this is the one. Okay, so this is, values of F. I don't know if you can read that. F equals 2.13, 2.14, and 2.15. 2.14 is what we found to be the bifurcation point. The 2D convective stability boundary is something like 2.06. It's not that close to this. And these are still, some of these are still stable. So the smallest one, 2.13 on the top, you can see, well, maybe you can't see yet, but we will see that, yeah, we'll move it up a little bit. So it formed a nice herringbone, but on top, you can see the herringbone is now being overtaken from the right by the shock. It's all entering the shock very slowly because these are not that, these true numbers are pretty close. So the bottom one is clearly going to be unstable and go to herringbone flow. The middle one is kind of very, very slowly going to become flat, I believe, but we never got there. The top one becomes pretty flat. Okay, so what's happening there? So this is interesting. It looks like we have a different stability boundary, but actually we don't. It took us a while to figure this out, but the next slide will really show what's happening. So here we'll just take no shock, just a laminar flow, just a constant state, and we'll put a Gaussian on it, and we'll see what happens. And now you see what happens is it firms up into roll waves to the right, herringbone to the left, and they're moving with slightly different speeds. And this is the whole story. The shock is really almost irrelevant. It's just like a boundary that's put in there, and anything that reaches the shock is destroyed. And if it doesn't reach the shock, it just stays happily and lives its life. And that's the reason. So, but this is not stability. I said that it was still stable. It really wasn't, because herringbones of any type are far from the shock. I would call it a metastability phenomenon. It's going far from the equilibrium, which was the shock, but then through some nonlinear mechanism is coming back after a large excursion. So that's the sort of thing we're seeing here. Oh, not in this picture, but in the previous picture. That's what we saw. It was just all that mattered was the relative speed of the roll waves and the herringbone to the shock. So if you have a situation where the roll waves are moving faster than the shock and the herringbone less fast, you'll end up with a herringbone pattern, a shock with herringbone to the left. But also, as you see, you can have a nice, certainly herringbone patterns can exist without any shocks. We just changed our reference frame to move with these herringbones. Okay, but all right, so that's that. And that really puzzled us for a long time, I must say. But because you have to think in a different way, it's not the usual kind of bifurcation theory. Yes, an essential bifurcation. Okay, now here's an important comment. Is okay. So now all the stability. There's a disconnect here. The spectral stability theory that I gave you was really in the whole plane. It was a Fourier wave number in Y, eta. But we have a channel. Okay, so it turns out, though, that the existence of a normal mode with the wall-type boundary condition is equivalent to existence of a normal mode for a channel of twice the width with periodic boundary conditions. So if we just had, so periodic boundary conditions are great. That gives you a Fourier series. And when people want to not deal with boundary layers, I've done this many times, just to get going, you put in periodic boundary conditions so that you can solve it. But it turns out that's actually the relevant one for this problem. And there are some precedents well, Kasimov and Stewart did some work in detonation where similar things happened in detonation. But I don't know how general it is, but it certainly worked here again. So that means we can do the analysis on the whole plane and then just restrict the frequencies to these discrete, just as we would for a periodic problem. And that will give us our, that's how we can do our spectral analysis. Okay, so so now that's the end of the 112 days. We weren't looking at every frequency in Y. We were looking at a discrete set. Okay, now very, very quickly, roll waves. What happens here? Well, we know less really, because up to now we didn't prove nonlinear stability even in 1D. But on the other hand, at a spectral level, it works out very well. Let's see. So, what's new? Well, the interior ODE, though I didn't mention it before, it becomes characteristic. It has 0 characteristic speed points, and that means it's pretty tricky from the standpoint of solving it as an ODE in X. It's a singular ODE. That made the numerics harder. There's also another dimension. Okay, so Zhao Yang did this. He did Frobenius theory, a series expansion near the singular points, and then a continuous ODE solver away. So matching these, and he got a very fast code in the end. It's actually faster than the one for shocks, which is incredible. And the results are, well, we were able to get numerically a complete 2D stability diagram, and it refines a lot the 1D case. And now, in the shock case, instability was essential. It was at high frequencies and an essential spectrum type. Here, there are instabilities, of course, because in 1D, there were already instabilities sometimes. Here, there are more instabilities, but it's of low frequency type. The first order rhythm is, again, hyperbolic, no help. You can get, we got second order by this miraculous degeneracy in 1D explicitly. We don't get explicitly in 2D, but we can numerically find it with care. And we see a bifurcation as we increase the width. So at width 0, if you take the width 0, you're taking frequencies very far apart. You've got 0 always in there as a transverse frequency, but it goes like 1 over the width is the next one. So as the width goes to 0, you're just basically moving out to high frequency. You're not seeing any of the low frequency. You won't see any instability. It behaves like 1D. But at a certain point, you get a bifurcation. But it's like point spectrum, basically. And it's not herringbone. It's something else. I think you'll like it. Let's come to that. Okay, we'll come to the bifurcation in a minute. Here's the stability diagram. Let's see. So what we can see is that there are some, let's see, what did I, it's basically very much smaller than the 1D. And these are different types of instabilities, the blue and the red. I won't go into that, but okay, so going back to the early numerical work and experimental work of Brock, his goal was to be able to predict when a channel will exhibit roll waves for particular height and flux and how high they will, sorry, particular flux and how high they will be. Well, this will tell you that if you know the width of your channel, you just look for the roll waves that are stable. Those are the only ones that persist. And then you can answer any question about their shape. So this is, in principle, very helpful. In practice, it turns out that I think we're pretty close to the 1D regime. So 1D was pretty okay for the physics. I'm sorry? Oh, yes, we have, sorry. We have the Froude number. You can barely see it. Yeah, the horizontal axis is Froude number. And then the minimum height is the vertical axis. And then the upper and lower stability curves were for 1D, the red and blue. And then we're filling that in with other kinds of instabilities. And there was a lot more instability. Let's see, but here's the good part. Okay, we'll finish with some humor. This is the bifurcation. Okay, it takes a long time to get going, so I'm going to jump us forward to a time about near 300. Okay, now we should start to see something. We called it flapping. It looks, if you look at it closely, they're not in sync. They're going one at a time. It's like doing the wave at the Jays game. And so that is a Floquet type Hopf bifurcation. So it's offset by the Floquet number. And the spectral analysis exactly predicts this shape. Those are the flapping. It's actually just a sinusoid moving up straight vertically up and down. It's kind of an illusion, but all right. So that we certainly didn't expect. But so there's a lot of rich behavior, but the roll waves have not much to do that we can see with the herringbone. Here's if we take a bigger width, then we get some really strange things happening. You'll see it can just go crazy and become chaotic almost. So that's, who knows? Period doubling to chaos, maybe, we don't know. But all right. Okay, so here I just really like this picture. This is from the thesis of Brock at Caltech, and he built this apparatus out of rain gutters, from aluminum rain gutters, or probably galvanized. And I believe this is the hallway at Caltech. You see the phone there, and these things are like 60 feet, and he painted them and put sand in the bottom. It's all homemade. It worked amazingly. I think, and then he did mathematical analysis on top of this to validate the corrector. And well, I think that must be one of the more complete and impressive theses in history. All right, so, okay, what about open problems? Well, we've got now a toolkit for multi-D, for general balance laws. We've got a heuristic kind of explanation of the herringbone flow. And what we'd like to do is to do a rigorous nonlinear stability and bifurcation analysis, validating all these rich things that we see. One thing that would be a very good start and is pretty accessible would be to linearize around the constant state and try to get a pointwise green function description of the early instability, like to find why are there roll waves in one place and herringbone in the other, to see this kind of asymmetry from the green function. And then the other one would be to work directly on the Richard-Gavriluk model. Okay, that may be ambitious. This would be numerical, but now this is getting to be serious numerics. It's 5 by 5 and not 3 by 3. So that's going to make everything take longer. But the good thing is that the Saint Venant gives us a very good start. So we've done this in 1D, and it gives you an idea what to look for, and so that helps you explore the parameter regime. And in many places, their behavior overlaps. So at least you have a start. Okay, and that's it. Thank you.
Thank you for wonderful talk. Any questions for Professor Zumbrun?
I guess this is related to the